You're live. Great. So we're shifting gears from kinematics, which is a description of motion, to dynamics, which is all about what is causing the motion, what is affecting the motion. And ultimately, a lot of us are concerned with how to control motion. We want things to go where we want them to go and not elsewhere. So there's a couple of different mathematical models that we can use to describe the control of motion. We're going to start out with the model of forces, which is based off of Newton's laws. And it starts with Newton's 3 laws of motion. Newton's first law is the idea of inertia. And the idea of inertia talks about what an object's natural state is. An object's natural state is constant velocity. Being at rest is a perfectly fine state that matches that, but it's not necessary. Being in motion at constant velocity is a perfectly good example of an object's natural state. So an object is perfectly happy to be moving. It is the act of changing velocity that an object does not want to do. If we want an object's velocity to change, we have to exert forces in order to do that. So the comma at the end is except when affected by a net force. Now, different objects have different amounts of inertia. Very light objects are very easy to influence, and very heavy objects are more difficult to influence. In the 1980s, there was this football player nicknamed the Fridge, William the Refrigerator Perry. He was gigantic, like 350, 400 pounds, and his motion was very difficult to influence. So on defense, when he ran into people, he tended to run over them. And that turned into be handy once in a while on offense. On a goal line situation, they would put him in as a fullback and tell him, just grab this ball and run through everybody. And it very often worked. So that's an example of the power of inertia. Now, Newton's first law makes mention of the idea of force. And force is one of the ways that objects can interact with each other. It's the basic mechanical interaction. So first, the intuitive stuff. Any act of pushing, pulling, or dragging something counts as a force. So if I push on this chair, that's a force. If I pull on the chair, it's a force. The carpet is exerting a dragging force on the chair, which makes my pulling, well, it resists against my pulling force. If the carpet was slippery, or if the chair was on wheels, then my pulling would do something slightly different. So pushing, pulling, and dragging are my typical examples of the way that forces can be exerted. When I first started teaching, I had to take a long drive to school, and I listened to the radio because I didn't have a smartphone yet. And there were ads on the radio, of course, and one of the ads was for a car dealership. And this car dealership had a push, pull, or drag sale, where if you could get your old wreck of a car into their lot, they would offer you some kind of trade-in value toward a slightly less crappy car. And every time I heard it, I thought about the fact that this car dealership is having their physics sale. These are the things that I connect in my mind. I connect words with between vastly different ideas. And another thing I like to point out about forces is that forces represent an attempt to affect the motion of an object. And the word attempt is there to stress that that might not be successful. So I could exert a pulling force on this desk and it doesn't go anywhere. But I exert the same pulling force in this chair and the chair does go somewhere. And if I exert the same pulling force on a rolly chair, then it'll move even more. So the force can exist regardless of whether anything is accomplished by it. And one other thing to remember about forces is that the actual effect of a force, if successful, depends on the direction of the force, and it depends on the relative direction. If you exert a forward force, that force is trying to speed up the motion. And if you exert a backward force, that is like retro rockets, then that is trying to slow down the motion. And the third possible direction is sideways, and that is a force that tries to redirect the motion of an object. Now, one of the most important ideas about Newton's laws and force analysis is that it's not usually just one force that tells us what's going to happen. It's a combination of forces. It's several forces. So if I push this chair sideways, I can get the chair to move. But if I push the chair downward, nothing happens. And that's because when I push the chair sideways, sure, there's some frictional force from the carpet, but it's not strong enough to resist completely my pushing motion of the chair. But if I push downward, then the floor prevents the chair from going any lower. If this chair was on, if it was like a floaty chair in a swimming pool and I push downward, it would actually go downward. But since it's a solid chair on a solid floor, it doesn't go anywhere. So we can't ignore the existence of other forces when we try to think about what happens when we exert our own force. And that brings us to Newton's second law, which is the mathematical thing that we have to analyze for the next 5 weeks of our course. So I like to actually write Newton's second law. F net vector is equal to mass times acceleration vector. And that is kind of the most bare bones version of Newton's second law that I can write and still say that it's correct. If I try to make it any simpler than that, then I'm really sacrificing some correctness somewhere. And I want to kind of go through these details that are in this equation to explain why it has to be that complicated. Now, the first part of it is the idea that that force is a net force, and net force is an abbreviation for the idea of total force. So we have to be able to add forces in order to figure out how to apply Newton's second law. Sometimes we do this addition symbolically, and sometimes we do this addition numerically. But either way, we have to understand what it means to add forces. And of course, there are the little arrows on top of our variables. These forces are vectors. So when we do this addition, we have to do it as vector addition. And that's why we spent a little bit of time over the last couple of weeks introducing vector addition, thinking about how it applies to velocities mostly, but occasionally in the homework we applied it to forces because they're just numerical vectors when it comes down to it. I want to jump to the end, and that is that the acceleration is what the net force actually causes. We don't have direct control over the velocity of objects. We don't have actual direct control over the position of objects. We have direct control over force and hence acceleration. And the easiest example I can think of to describe the difficulty that we face when controlling acceleration is thinking about how do I move this thing, this pendulum that's hanging from this position over to here. So I can just move my hand over to there, to a new position, but now it's swinging back and forth because I controlled the position of my hand because I've been interacting with my hand since I was, a few months old. I know how to exert forces with my muscles to make my hand go where I want it to go. But I have not been interacting with hanging objects all that long. So how can I get this object to go from stationary over here to stationary over here without it being swinging at the end? I can move it slower. That works pretty well. There's still a little bit of swing, but it's not too bad. I can grab it and control it much more directly. That's called applying a constraint force. A constraint force is a special kind of force that gets to be stronger and weaker exactly as you need it to be. It's an adjustable force.
You could swing it over and then do like a PID control?
So I can very deliberately try to stop its motion at the desired point. This motion is actually symmetric, forward and backward in time. I can obviously start it fairly easily, but it's the stopping that's a little bit harder because starting, I do stuff and then it reacts. When stopping, I have to predict how it's going to react ahead of time. So I could go across and then start slowing my hand down ahead of time and kind of try to absorb the velocity at the right moment at the end in order to get it to stop where I want it. And for electrical engineers, you're almost certainly going to learn about the idea of a PID control, which stands for proportional, integral, and derivative control of something, where you are measuring some quantity like temperature in a room, and you're controlling some other quantity like the amount of power going to a heater. And you want the temperature to get to a certain point and stop there. So you turn your heater on if it's too cold, and you have to know that as the temperature is approaching the right value, you may need to turn the heater off a little bit early so that the temperature finally settles on the value you want. Or if your temperature is way too low, you may need extra heat in order to actually get to where you want to go. The most common type of control that we tend to interact with is the cruise control in our cars. It's actually pretty good at setting the velocity of the car and adjusting to wind and going uphill and downhill and stuff like that. If you're the passenger in a car that is operating under cruise control, you can watch the gas pedal move as the cruise control adjusts things. I don't recommend looking at the gas pedal while you're the driver. It's probably not a good idea. So the final quantity here is mass, the m value measured in kilograms. We talked about that on units day. Is a difficulty factor in this equation. So this equation is kind of like saying the effort we have to exert is equal to the difficulty of the task multiplied by the amount of the task that we want to accomplish. And there's a lot of equations in physics that are of that form, that effort is difficulty times accomplishment. In fact, I feel like I may have heard a motivational speaker say those words at one point or another. Now, the force in this equation, or the forces that get added up, are measured in newtons, which is an abbreviation. 1 Newton is equal to 1 kilogram times 1 meter per second squared. We would not want to write kilogram meter per second squared every single time we talk about forces, so we've abbreviated it to the Newton. Mechanical engineers like to use other units of forces. We tend to have a unit of force called the pound, and there's also a unit of mass called the pound. In SI units, the unit of mass, the kilogram, and the unit of force, the Newton, are distinctly different from each other. And we'll talk about how they are related in different situations. In English units, the pound force and the pound mass are very closely related to each other. A mass has a particular weight, and the pound force is the weight of a pound mass on Earth. If you take a pound object to the moon, it will still be a pound mass, but it will no longer weigh a pound. It will be a lot lighter because on the moon things are lighter. Now I want to talk about Newton's third law. And Newton's third law is about how forces on different objects are related to each other. Now, in my mind, when I'm thinking about two objects exerting forces on each other, there's really only one interaction between the two objects. Think about the interaction between me and the Earth. I am pulled down to the ground by gravity due to the Earth. And to me, that means that the Earth and I are attracted to each other by this force of gravity. So I feel a copy of this force that pulls me downward. The Earth is affected by an opposite copy that pulls the Earth upward. Now, the result of these two things is completely different. I am held down to the ground. It's pretty difficult for me to jump or fly, whereas the Earth doesn't really care that I exist. So, Newton's third law is about a balance between the forces, not a balance between the results. It's important to keep that in mind, but it is an absolute balance between the forces. I don't know of any exceptions to Newton's third law. So that's going to become important later on after exam 2 when we talk about momentum and the fact that momentum is absolutely conserved in the universe, and we can't get momentum from anywhere but from other objects. Now, if I wanted to write this down as a mathematical rule, I would say something like F12 is equal to minus F21. And here's some examples of pairs of forces. We could have a repulsive force where the two objects are pushed away from each other. We could have an attractive force where the two objects are pulled toward each other, which is the gravity example I gave. And then the third direction that we could have is a shear force, where we have our two objects probably in contact, and one object feels a force that way and the other object feels a force that way. So repulsive and attractive forces are easy to think about as far as directions go because they represent the idea of pushing and pulling. The shear force has the objects lined up in one direction, but the forces are in the perpendicular direction. That's what makes a shear force what it is. And these descriptions are nice because I can use the same word to describe both copies of the force. If I wanted to describe this force here, I would have to say awkward things like the force on the left object is leftward. That's just too many words when I could just say these two objects repel each other. It's even worse for the attractive force where I have to say the left object feels a rightward force and the right object feels a leftward force. It's just too many words. The objects attract each other is much easier summary to use. So that's a little bit of the background of forces, kind of a broad introduction to forces. We really are in here to do some analysis of forces. So let's go ahead and do that. Our main tool to begin our force analysis is a graphical technique called creating free body diagrams. So we're trying to analyze F net vector is equal to ma vector. And the big complication is that F net is an addition of vectors, and it has to include all of the relevant vectors and not include any extras and not duplicate any. So there's really kind of an accounting task here to make sure we get the right things into our equation. And as it turns out, we're not really all that good at accounting, so it's useful to have some graphical techniques in order to get us through it. So here are the elements that go into a free body diagram. There is some object, the mass, that we're considering, that we're thinking about. The object should be part of our free body diagram. We have to include all of the forces affecting the object. Sometimes we may need construction lines. Construction lines are like direction references so that we can talk about angles, because in order to have an angle, you have to have an angle between two lines that cross. So construction lines give us the ability to label angles. And then we have to have a well-defined coordinate system. Sometimes after we draw a few free body diagrams, if we're just using the regular XY coordinate system, we won't draw it because it takes up space and effort. But if you're using a different coordinate system, you definitely have to draw the coordinate system. And then, of course, we have to have labels. Otherwise, what's the point of making a diagram? Because the purpose of the diagram is to tie the reality of the situation into an equation that contains lots of variables. And the diagram is what gives us the ability to mentally connect the pictures with the symbols. So let's think about an object, M1, that is sitting on a scale. And in turn, that scale is sitting on a table. This is not a free body diagram. This is a system diagram. It's a sketch. It's a schematic of what's going on. It's really important for me to understand the situation. It's kind of like a graphical description of the overall scenario. So I've drawn a picture of the overall scenario. Pretty useful. Here's my free body diagram. There is my object, M1 with a label. Now I need to think about all forces affecting the object. A force is anything trying to move M1 or prevent M1 from moving. So definitely we have gravity. Gravity is trying to make M1 go toward the center of the Earth. So we label it with an arrow, and I always call gravity F subscript G. Now, a force isn't just something that tries to make something move. It can also be something that tries to prevent something from moving. It can be acting against another force. So this thing is being lifted up by the scale. Gravity's pushing down, the scale pushes up. So we have a force heading in the other direction. This is called F sub n. Anytime you have solid objects in contact with each other, they should be exerting a normal force on each other. If you do a calculation and you find the normal force goes to 0, it's because the contact stops. So that's one of the mathematical criterion we can use to describe when an object leaves another object, when a car leaves the ground. And the reason it's called a normal force is because one of the definitions of normal in mathematics is perpendicular, and this normal force is perpendicular to the surface of contact. So then, at this point, I have my free body diagram. I can think about my F net vector is equal to MA vector. And I can read off the list of forces from my free body diagram. Fn vector plus Fg vector is equal to M1A1 vector. So here I have made everything in the supergeneric equation just one level more specific to my particular case. Sometimes you won't write both of these equations. You'll just write one or the other to express that you have started doing force analysis. My Fnet, I broke into a total of 2 vectors. My mass, I used the specific label for this diagram. And my acceleration, I indicated that, hey, this particular object, object 1, has its own particular acceleration. So now I can start to incorporate more detailed knowledge of what's going on here. This is a vector equation, and usually to analyze a vector sum, we take components. So all of the activity in this diagram is in the y direction, so I'll take y components of everything. My normal force is in the plus y direction, so it is itself. My gravity force is in the minus y direction, so that's the point at which it becomes a negative. This object's sitting on a scale. Usually when you weigh something, when you sit on a scale, you kind of wait until it's stationary. If something is at rest, it has 0 velocity and 0 acceleration. So now's a perfectly good time to plug in that 0 on the other side of the equation. So now we're at the point where we can actually solve for something. and get a relationship that says Fn is equal to Fg. In order to go further, we'd have to have a little bit more knowledge of one of these things. We could get more knowledge of the normal force by looking at the scale. So we could do an experiment which would tell us the value of the normal force, and thus we would know the value of the gravitational force. The gravitational force, if you're on Earth, depends on the mass of the object. And every object on Earth has the same proportionality factor. It's kind of neat. So our force of gravity is equal to mg, where g is the same number you've been using before, but I tend to write it in newtons per kilogram. Now, last week there was a group that brought an instrument to campus called a gravitometer, which measures G. I think their gravitometer measures it to 9 digits of accuracy. Did I talk about this to you guys? Yeah? They were dropping stuff, yeah. They basically had this mass that was bouncing off a spring, and when it was in mid-flight, they bounced a laser off that measured the G value. That's all that more accurately I care to measure G, because it does vary. I think their instrument was accurate enough that the tides and the change of the water table due to rain is measurable. So they coordinated with somebody in water research who has wells around campus, who actually measured the water level so that they could see exactly what the correlation is between the gravity measurements and the water table measurements. I think this is the most accurate gravitometer that exists. I don't think we can measure it any more accurately than that.
How big is it?
It was about as big as a surveyor's tripod, but the actual instrument, there was a bottom section that was about 1/2 meter, and the top section was about 20 centimeters in diameter. And it's a vacuum tube, so they sucked the air out of it and kept it running throughout the entire measurement, kept the vacuum pump running. There's a portable version that they had for, mostly for surveying, that is about the size of a lunchbox, maybe a large lunchbox. But the big one had an accuracy of 1 microgal, and a gal is a Galileo, which is a centimeter per second squared. So 1 microgal is actually 10 nanometers per second squared. The little ones only have an accuracy of like 50 nanometers per second squared instead of 10 nanometers per second squared. So the big one's 5 times more accurate, probably 20 times more expensive. So now we have a very common result where F sub n is equal to mg. And it's important to remember that this is not an always equation. This is the result of analyzing this particular situation. Now, it's a very common situation, but there are certain assumptions and certain knowledge that's built into this analysis that needs to be true in order to keep this result true. So what are the things that I built into this analysis that we could possibly break, that we could change to make the result no longer true? How did I get from generic equation to here? What's one of the things I did along the way? That there is a normal force. Okay, that's one I hadn't thought of. I'm still on that one. I was only going to list 3 things, but now I have to list 4 things. Yeah. Yeah, that's good. Okay. Definitely also has to be true that we have 0 acceleration. So that makes me think of, how could I have a different acceleration other than 0? Any idea? It's moving. How could it be moving? What? Well, another force is a third bullet. I still want to go back to, how can we have a non-zero acceleration? It's moving. Constant velocity is still 0 acceleration. I want to break 0 acceleration. How can I physically do it? I don't want to add another force. So it's just...
What if you drop it?
If I drop it, what if I don't quite drop it? What if I just lower it? Controlled. What if this entire thing is in an elevator? So then the object, the mass, is still sitting on a scale, but because it's rising and falling with the elevator, there's some acceleration. As it turns out, most of us have a normal force measuring device in our pocket. My phone has a sensor called an accelerometer in it. And the accelerometer doesn't actually measure acceleration. What the accelerometer measures is normal force. So there's some little mass in there, and it's measuring the normal force required to hold that little mass. And if you go up in an elevator, you can produce a graph that looks kind of like this. F sub n versus t. At first, it's constant. So that little mass requires some force to hold it in place. When you first start out in the elevator, you need some extra up force, which means some extra normal force. But then once you're at constant velocity, you're back to 0 acceleration again. So you can have regular normal force. Normal force, if you allow me to say that. Then you get to the top and you want to slow down again. With positive velocity, it requires negative acceleration to slow down, which requires less normal force. Then you stop at the top and the normal force goes back to regular again. So I actually did this experiment. I lost track of the data file. I'll have to do it again. But the graph really did look kind of like that. There's noise on it. I kind of smoothed out the noise. But the normal force actually increased for a time and it decreased for a time. So we have 3 options so far we've discussed. In order for the normal force to equal mg, there has to be a normal force. You have to have no acceleration. You have to have no other forces interfering with that equation. In other words, no other force with a y component. There's one more assumption that's built into this analysis. Sure, but you could always adjust g to be a different value. When you take components of vectors, very frequently you end up with sines and cosines. I did not have any sines and cosines because my normal force is up. That was part of the model. And if you make a situation where the normal force is not upward, then you break this model. So imagine an object on a crooked scale. Then the normal force tilts. And then this entire analysis breaks down. So the reason I like to go through all of this is because I want to stress that that idea that the normal force is mg is very common. You should jump to that conclusion when it's appropriate. You should not do this analysis every single time. But you also have to keep your eye out for anything that might break this analysis. And specifically, non-zero vertical acceleration, other forces, or a tilted normal force. And then you should no longer jump to this conclusion. You should do the appropriate analysis to figure out how your normal force is related to the weight of the object. All right. I think we have done enough for today. Homework 3 is going to appear sometime in the next couple days, probably before the next class. It won't be due this weekend. It'll be due the following weekend. Actually did spot the administrative errors. What did I do?